lock from the resources. All right, and what is the next thing which we will be allowing here? We will allow others to know that the critical section is over so that they can come ahead and place the request to enter in that. Okay, so we can say, and let the others know that its critical section is over. So I assume with the help of this, you will actually develop the understanding about how the critical section is going to be executing. All right. So what and all do we have here? Firstly, we have the entry section, then we have our critical section, then we have exit section, and at the last we have remainder section. So your entry section is actually going to be controlling the entry of your entry in the critical section, and it is also going to be providing lock on the required resources. Then you have critical section, which is actually your critical part. Then you have exit section, so it is actually going to be removing the lock from your resources, and it will also let the other people know that I have exited from there. And once if they will know that, so they can actually come ahead and place the request to enter in the critical section. And your remainder section is going to be having the remaining sections, whatever you are going to be having. Okay, so now let us discuss the next thing. So what is the next thing which we have? That okay, we have discussed about the critical section. Now we should be discussing about the ways we can actually solve that. Okay, so our next topic is going to be solution to critical selection problem. All right, so here what and all we are going to be having. So what is the solution here? So the first solution which we have here is the mutual exclusion. So the first one which we have is mutual exclusion. So what is the mutual exclusion doing here? So this particular one is actually see that okay, if one process is there in their critical section, so it is not going to be allowing any other process to enter in the critical section. So that is what is the meaning of your mutual exclusion. All right, so the second one which we have is the bounded waiting. So what is the meaning of bounded waiting? So let us say you have various processes which are executing. So every process is also going to be having some of the time for their execution. All right, so what we will be doing, we are going to be providing a bound on the number of the times that the other process are allowed to enter in their critical section after they have made a request. So you know how it is actually going to be working. So let me first write down bounded waiting. So let us say, like I'll give you a very small example based upon this. So let us say you're going outside to have your food. So what happens sometimes you act let us say if it is completely booked, so what happens, they will say I will be entering your name in the waiting list. So basically what happens if somebody is eating their food, so as long as they're eating, you're not allowed to enter there. But once they are leaving from there, they will start just calling you people based upon the order in which your name is there in the waiting list, right? That is how it happens. But sometimes what happens when the waiting time is actually greater than 1 hour or 2 hours, so what happens, people just start roaming here and there. So people usually call them that okay, we have a table available, you can come here and complete your food. But they cannot just wait for them forever, right? They usually give them some bounded time that okay, we'll be waiting for this person for 10 minutes or 15 minutes. If they are not turning up, then they assign it to the next person who is there in the waiting list. So same here when we talk about the bounded, this is bounded actually. So we can say about bounded waiting that if you are actually having a scenario of bounded waiting, so what is going to happen in such a case, they are going to be waiting for some definite time, some bounded time, and after that the request which they have there, they are actually going to be granting it to the next one which is there in the list. All right. The next one which we have here is the progress. So what is the progress saying? So let us say you are going to be having some of the processes, right? Let us say there is a scenario where no process is executing in their critical section, and some of the processes are actually there who are waiting to enter in their critical section. So what is going to happen? So those processes who are not executing in their remainder section, they can only be participating in the decision depending upon who is actually going to be there in the critical section. And this particular thing is not going to be postponed indefinitely. That is how they are going to be making the request. So what is going to happen if no process is there in the critical section and some processes want to enter in their critical section, so only those processes who are in the remainder one can actually go ahead and make the request for entering in the critical section, because they have already done the request. That is the reason they are in the remainder one, and that is the reason they are going to get prioritized. Same like how I was giving you the example of waiting. So let us say some people who are turning up to the restaurant, but they are not going to be allowing them. Who are going to be allowed? Those ones who are there in the waiting list. So that is how we can actually provide solution to your critical section problem. Now we have various solutions available to us. We are going to be discussing about it. All right. So the first one which we have is called as Peterson's solution. All right. So in the Peterson solution, what actually happened? We are going to be having some software based solution to enter. Like we will be having, I told you about the critical section problems. So here we are going to be having some solution based software based solution for that. Okay. So what this one is, firstly, it is widely used. And the second one is, here we will be having software based solution to critical section problem. All right, in this particular one, like why it is actually named as Peterson, because this is named by the computer scientist whose name is Peterson. Okay, so in this particular one, what actually happens? So let us say somebody wants to enter in any of the critical state. So at that particular time, the other process only executes the rest of the code and vice versa. So what is actually going to happen? We will be actually ensuring that if like only one process is there which can run in the critical section at a particular time. So we are not going to be allowing each and everything. Okay, so let me just write it down here. So what does it offer? So it say that with the help of this solution, whenever a process is executing in any critical section, then the other process only executes the rest of the code and vice versa can happen. All right. Also, what is going to happen when we are going to be talking about this method? So this method is also going to be ensuring that only a single process can run in the critical section at a specific time, and that is what our requirement was there, right? So we can say this method also helps to make sure of the thing that only a single process can run in the critical section at a specific time. All right, now if you remember, we discussed about the three solutions. So this particular, we discussed about three of the conditions which we require. The three conditions which I have mentioned here. All right. So this Peterson actually ensures all of those things. So when we talk about the mutual exclusion, so that is also taken care here. The bounded weighting is also taken care here, and the progress is also taken care here. So here what actually happens, so let us say we have some n processes. Let me just write down here. So let us say we have p1, p2, pn, some n processes we have. All right, and let us say at some point everyone wants to like, let us say there is coming a point where every process needs to actually enter in their critical section. So what we will be doing, we are going to be creating one Boolean array. So since it is going to be Boolean, what we will be doing, initialize, we will be initializing it to false initially. And once like let us say if any of the process wants to enter in the critical section, what we will be doing, against to that we are going to be setting as true. So what is going to be helpful, based upon those entries in the array, we are going to be determining who and all is actually waiting for their execution. Apart from that, we are going to be taking another variable which we are going to be naming as turn, and what this turn is actually going to be doing. So this particular one is going to be telling the process number. So we can say it tells the process number that is waiting to enter into the critical section. All right, so based upon that, we will have the process number also available to us. Okay. Apart from that, what we will be doing, so the processes who want to enter in this critical section, they will be changing their turn to any other number, and based upon that we will understand that this particular process is waiting for its turn to enter in the critical section. All right, so let us say we have various process, just change that turn to something else, and based upon that we will understand that this process is waiting for its execution in the critical section. All right, now we are going to be discussing about synchronization hardware. All right, so what is a synchronization hardware? So we are going to be having various systems, and all those systems are going to be providing the support for the critical section code. So we can say many system provides hardware support for critical section. All right, so what we can do in this situation, also we are going to be having the critical section problem. So the critical section problem we can actually solve by using a single processor environment. So we can say critical section problem can be critical section problem can be addressed by single processor environment. All right, so how this one is actually going to be helpful, when we will be having a situation where we have multiple hardwares who want to enter into the critical section. So in such a case, your single processor environment is going to be helping us. But it will be doing, it is going to be performing the interrupts which can actually be available on the shared variable when it is going to be modified. So what we will be doing in such a case when we are disabling them, so at that particular time we will understand that, let us say you want to use a file at a point, if it is actually disabled, so what is going to happen, you cannot actually go ahead and use it because it is disabled, right? So it is not going to be creating any such issue. All right, but at the same time, if you will keep on enabling and disabling it, so that is going to be consuming a lot of your time, because it is also going to be taking up some of the time in enabling and disabling, right? So here what will actually happen, it is actually going to be like we are going to be sending the process to all of the processes, right? So since that enable disable process message sending time is going to be greater, so in such a case we can also expect some of the transmission lags for the processes to enter in the critical section. And what will actually result then, the entire system efficiency is going to be decreasing. So what is actually happening here, we are using your disable, we can say disabled or disabling, I'll write. So we will be using some disabling interrupts. All right, so if we are sending those if we are performing any disabling, so we are sending some of the messages to all of the processes which we have. Okay, so send message to all process. So obviously if we are sending it to all of the process, what we will have, we are going to be experiencing some transmission lag delays. All right, and because of that, what will happen, your system efficiency will decrease, which is not actually desirable. All right, so in this particular one, we even though this is coming up with some of the solution, but what we can say, if you are having a multiprocessor environment, in such a case this solution is not a feasible one, because here what is actually going to be happening, we can be sure about what the current sequence is going to be there, but at the same time, because of these disabling interrupts, it is actually going to be taking a lot of our time, and that particular one is going to be affecting the entire efficiency. All right, the next one which we have here is semaphores. So now if we have to talk about semaphores, so what are the semaphores? And this is also some of the times people also ask these things in the interviews. All right, so what are the semaphores? So you have the problem of critical section problem, right? So what semaphores are going to be doing, so whatever that solution is going to be there, so in that particular one, we cannot actually guarantee that we can actually we cannot actually guarantee that we will have more complex problem. We can have complex problems, we can have simpler problems as well, but if we are going to be having some of the complex problem, so if you have to deal with it, you will actually be making it more complex. So in such a case, if you are going to be making them synchronized, in such a case your task can actually ease out. So what we are actually going to be doing here, if you have the complex problem, just synchronize them. And if you are achieving these two things, so overall what we are doing in such a case, we are these two things are actually going to be there in your synchronization tool, and that particular tool is known as semaphore. So based upon this tool, we are overcoming this difficulty, that if you have a critical complex problem and if you want to perform a synchronization, so with the help of a synchronization tool, which is called as semaphore, you can overcome this disability. So basically what it is going to be there, so you can consider a scenario that you have a parking lot. All right, so what is going to happen? Some cars are going to be there. All right, now let us say one more car is coming. So what will happen? Now this car wants to perform a parking, but we do not have any of the space in such a scenario. So what will we do? We are going to be waiting for someone to remove their car, and then only we can go ahead and perform it. So in such a scenario as well, we are going to be using the situation of semaphore. So semaphores are actually going to be helping us out. So how semaphore will be helping us in such a scenario? So it is actually going to be like, here we are going to be using a variable, and that variable can hold only non-negative integer value, and that one we are going to be sharing between our different threads, and those threads are going to be running on the operations which will be of wait and signal. So we will have a variable which can actually like, I can actually write it in a better way. We can say that semaphore is a variable that can hold only a non-negative integer value shared between all the threads with operation wait and signal. So just now I spoke about the parking lot. So here also how you are actually going to be performing based upon this wait and signal. So if you are going to be waiting, in such a case, you can just wait and hold for some time. Once you are getting a chance, you can go ahead and perform the execution. Now I will be actually showing you how does the wait operation works. So for the wait operation, what is the code we actually use? So let us say we have a variable s for the semaphore. So we will have wait. So this one is going to be there in the wait function, and inside that what will happen? While your s is actually less than or equal to 0, in such a case, you are not going to be performing any operation. So do not perform any operation in such of the scenario, and what you do, just keep on decrementing it. So that is how your wait operation is going to be there. So here what we are doing, we are decrementing the value of our argument s, and as soon as it is going to be becoming a greater than or equal to 1, in such a case it will keep on executing it. All right, so how this operation is actually going to be helpful for us? So this particular one is going to be actually controlling the entry of a task into the critical section. So we can say this controls entry of a task in the critical section. All right, also in this particular one, your wait operation is actually going to be helping you in ensuring that if it is there in the critical section, then we are not going to be making it enter there. All right, now I will be talking about the signal operation which we have. So your signal operation. So we will have a signal s, and here what we will do, we will be incrementing your s. So here what we will do, we will be incrementing the value of our argument, and here what we will do, in this particular one, no more processes will be blocked in our queue. All right, so we can say increment s as no more processes are blocked on the queue. All right, Also in this one, what we will be doing, we are going to be like how this signal is actually going to be helpful. So this signal is going to be controlling the exit of a task from the critical section. So we can say this controls exit of a task from the critical section. All right, so this is how this one is going to be helpful and how it is actually helpful. So we are going to be ensuring that if you have a process which is actually modifying the value of the semaphore, because here you can see in both of the processes what we are doing, we are actually going to be dealing with your semaphores. All right, so what we will be ensuring here, we will say that when one process is modifying the value of the another semaphore, so what will happen in such a scenario, no other process can actually at the same particular time, no other process can actually go ahead and modify the semaphore's value. And then what will happen, we will be entering in our exit section. So then your signal operation is going to be working. So in that one, we are just going to be updating it. And since this one is going to be just controlling the exit, so we can go ahead and exit from it easily. All right. Now we will be discussing about some of the properties of semaphore. So properties of semaphores. So what do we have in our semaphore? So here we are going to be working with the many processes. This one, like obviously all these things are going to be arising when we will have the multi-process scenario. So here we have multiple processes. All right. Also, what is going to happen? Whatever things how we are actually addressing. So if you remember in the semaphore, what we are taking a value which is a non-negative integer value. So we can say semaphore value is a non-negative integer value. All right. Also here what is actually going to happen, you can have different critical section and those different critical sections can be there with the different semaphores. So what is actually happening, we are allowing more than one process to complete its execution at the same time, but we will ensure they both are not going to be dependent on each other. Okay, so we can say different critical section with different semaphores. All right, and in this particular one, every critical section is going to be having a unique access to the semaphore, because if it is not going to be uniquely available, again it is going to go in the critical section only, right? Sorry, it is going to go in the deadlock situation. So we can say each critical section has unique access semaphore. All right, so here since we are having the multiple processes and if we have multiple critical sections, so all that is actually achievable. So we can say it allows multiple processes into the critical section at once. If required. All right, so this is how you will actually understand that what and all are the properties of the semaphore and how we are going to be addressing them. Now we are going to be discussing about the different types of semaphores which are available to us. Types of semaphores. So we have two types of semaphores. So the first one which we have is the binary semaphore And the another one which we have is the counting semaphore. All right, so in the binary one, what is going to happen? Like the binary thing is, binary things are always in the terms of zeros and ones. So here it will take the values zeros and ones. All right, so what is going to happen in this particular one? We are going to be implementing the mutual exclusion. And when we are going to be doing it, we are going to be using mutex. Okay, so let me just write down small things about it. Binary semaphore. So we can say here what we will be doing, we are going to be implementing mutual exclusion. And since like if you will just use these words, mutual exclusion. So based upon these words, we have actually came up with word mutex. All right, so what we can do, this is because of this it is also called as mutex. And in this particular one, what is going to happen, whatever your binary semaphore is there, that will be initialized to 0, and it can take only values of zeros and ones in this execution. So we can say initially, or we can say initialize to 0, sorry, initialize to 1, and it can take values of zeros and ones during the execution. All right, so that is how it is going to be working. So you know, if you are having the value, so we were discussing about your wait and signal. So your wait can actually work if the value of semaphore is 1, and your signal can work when the value when the value of the semaphore is going to be 0. So wait will work with a semaphore value as 1, and your signal can work with a semaphore value of 0. All right, that is how it is going to be working. And these binary semaphores are actually easier to implement as compared to your counting semaphores. Okay, now we are going to be discussing about counting semaphore. So what and all do we have in our counting semaphore? So in this particular one, we are going to be implementing the bounded concurrency. Okay, so we can say this one is actually there for your bounded concurrency. All right, so here what is actually going to be happening, we are going to be having one unrestricted domain. So in the previous one we had 0 and 1. Here we do not have any of the control over the count. It can have any value, and these ones are actually used so that we can provide access to the resources. So we are going to be having some finite number of resources. This particular one is going to be there in order to provide access to those resources. So here what is going to happen, we are going to be having something like semaphore count, and that particular count is going to be indicating the available number of resources. So we can say we have semaphore count, which will give you count of the number of available resources. All right, in this particular one, what we will be doing, so if the resources are added to the semaphore, so it is going to get incremented. If the resources are removed, in such a case, it is going to be decremented. And counting semaphores have no mutual exclusion. So we can say counting semaphores have no mutual exclusion. Whereas if we talk about the binary one, so there we were actually having the mutual exclusion. All right, so now I will be just sharing you some of the code for the same. So let us say, like I can actually say stepwise implementation of invoking declaration and usage of semaphores. All right, so here what we will be doing, we are going to be first of all declaring a mutex. Okay, and that one is going to be a shared variable. So we will write it like shared var mutex. Okay, so here I'm going to be initializing it to 1. Okay, after that what I will do, I'm going to be beginning my process. So here I will have a process I. It will vary. All right, so then we will have begin, and after that we are going to be performing some of our code here. After that, this one is going to be performing mutex. Okay, after that what we will do, we are going to be executing your critical section. All right, after that we are going to be running v mutex, and after that what will happen, after executing it further, we are just going to be exiting from there. So based upon that, it is going to be performing the execution. So you can see this is how your code is actually going to be there, and this mutex is actually the variable which is actually shared between both of them. Okay, now we are going to be discussing about the advantages of semaphores. Okay, so in this particular one, obviously if you are having some of the resources, so basically what you are trying to achieve by using semaphores, you are providing a management to the resources, and that management is going to be flexible. So we can say provides flexible management of resources. All right, in this particular one, what and else we are going to be having, so we are not going to be allowing multiple processes to enter in their critical section. So do not allow multiple processes to enter in the critical section. All right, here what is the next thing which we can talk about semaphore, that your semaphores are going to be machine independent, and they should be running in the machine independent code as well. All right, also if we are going to be saying that they allow more than one thread to access the critical section, they allow it, but by providing the different values of semaphore. Okay, so we can say they allow more than one thread to access the critical section. All right, also in this particular one, we are going to be following the mutual exclusion property, and that one is actually extremely important because that is something which is actually desirable in order to solve the critical section problem. So we can say it follows mutual exclusion principle. All right, and in this one, since everything is so well synchronized, so we are not going to be having wastage of resources. So we can say no wastage of resources. All right, now we are going to be discussing about what and all are going to be the disadvantages of semaphores. All right. So you know what is actually going to be happening here. In this one, what is the biggest limitation which we have with the semaphore? That we are going to be leading to the priority inversion. And what happens in the priority inversion? Low priority processes will access the critical section first, and the high priority may access the critical section later. So that is one of the major disadvantage of the semaphores. We do not want such a thing to happen. But since we are not having any priority inversion, so that is the reason it is going to be it is just going to be executing in that odd manner. So we can say it may lead to priority inversion. Okay, so we can say low priority processes may access the critical section first and high priority may access the critical section later. All right, also in this particular one, what is our major thing? To avoid the deadlocks, right? So here, to avoid the deadlocks, what we will be doing, we are going to be using wait and signal. And when we are going to be executing wait and signal, we will have to ensure that they are also getting executed in the correct order. So we can say wait and signal should also be executed in the correct order. All right, what is the next thing? So here we are going to be, when we are going to be talking about the semaphores, so if we are going to be talking about semaphores on the large scale, so that is going to be little impractical, because their usage is actually going to be leading to the modularity. And why it is actually going to be working? Because we are using two functions here, that is wait and signal. So what that one is going to be doing, that one is going to be preventing the construction for the structured layout. And structured layout is actually desirable. If we are not going to be achieving that, it is not going to be providing the best results out of it. So what will actually happen? We can say that we can use it, but this is not the conventional way of using it. And if we are going to be performing it with the improper use, so what will happen? It may actually go into the block state, and such a state we refer it as deadlock, and deadlock is something which is not desirable. All right, now we are going to be discussing about some classic problems of synchronization. All right, so what and all are some of the classic problems of the synchronization? So we basically have three problems, and what and all are the problems of the synchronization? So you know, when we are going to be talking about the semaphores, what will happen? We are going to be taking care of the synchronization apart from the mutual exclusion. Mutual exclusion is still going to be there, but apart from that, we are going to be looking into the synchronization problems. Okay, and because of that, what we will be doing, we are going to be taking care of three of our problems. Let me just write down three of them here. So the first one is going to be bounded buffer, and this one is also known as producer consumer problem. All right, what is the next one which we have here? That is going to be dining philosophers problem. And the third one which we have is the readers writers problem. All right, so all these problems are going to be actually, like, we realize that these three are actually having some of the flaws in your process synchronization, where the system was actually present.